Implicit differentiation is a super fun topic. And before I actually show you what it is and how this works, I would ask that you just think about this word and what this means, because it will shed some light onto the nature of how we proceed. The word implicit in our language is the opposite of explicit, which means a number of things, but one of the things that explicit means is that whatever it is that you're talking about is stated clearly. It is, there's no room for confusion, there's no doubt, you know what you're looking at. So if something is implicit, we get this idea that maybe it's a little more confusing, right? Or less clear. So in the world of mathematics, how this manifests itself for us in terms of an equation that is implicitly defined versus explicitly defined is this. Most equations that we look at are in the form of y equals some stuff, right? So for a quadratic, here's a quadratic. And this is an explicitly defined equation. We don't really call it that ever. I don't know that you've ever called it that up to this point in your math career. But that's what it is. It's explicit because there is no room for confusion about what y is equal to. Y is equal to this x squared plus 4x plus 17 defined in terms of x. So the question arises, what would it look like for an equation to be implicitly defined? And the answer is, anytime that you've got x's and y's kind of garbled up together like this, you have something that is implicit. This is an implicitly defined equation. So we're going to look at how do we differentiate something that looks like this. So before I teach you how to differentiate an implicit equation, let's just go ahead and give ourselves sort of a casual, informal definition of what an implicit equation is. So it's really any equation in which x and y are mixed together. So typically they're not solved for y. And if they are solved for y, if it's like this, you could still have, sorry, this is not y prime, that looks like y prime. Let me erase that. If you have, you could have an equation that's like y equals, x times y squared plus 4y. Even though this thing says y equals, this is not explicit because y is still showing up on the other side of the equation. It's all garbled up. So anytime that you've got that going on, you have an implicit equation, and whenever you have an implicit equation, you need to use implicit differentiation in order to find the derivative. So the key to unlock the world of implicit differentiation is a little tiny piece of notation that is going to be new to us starting right now, and it was notation that was developed by this guy Leibniz. If you remember back from like the very first video, Isaac Newton and Leibniz both got credit for developing calculus ideas, but one of the things that was unique to Leibniz is that he developed this specific notation called dy dx. Sometimes this is referred to as infinitesimal notation, and let me explain a little bit more about what this thing actually is, because this is going to be the key to unlock the door of implicit differentiation. So we've already talked about the fact that if you have a function f of x, its derivative is f prime of x. If you have a function y, its derivative is y prime, or dy dx. We've mentioned this, but we haven't actually unpacked this. So let's take a step back. First of all, just recognize that this thing is a derivative, and what it means, what Leibniz was trying to get at, is this d stands for derivative. You can sort of think of it this way. What we have is the derivative of y over the derivative of x. And intuitively, this makes some sense when you compare dy over dx to a change in y over a change in x. What we're finding when we find our derivative is an instantaneous change in y over an instantaneous change in x, and that is that's what's being captured in this notation. We're finding an infinitely small change in y over an infinitely small change in x, and that is what this notation is showing us. So So that is the final derivative, but you're going to see this thing in another form. d over dx. When you see d over dx, this is the incomplete version of dy over dx. And what this thing is a command. It is an imperative. It is not a suggestion. When you see d over dx, what this thing screams at you is to find the derivative. This means find the derivative, and there's one other piece here, and it's that we need to pay homage to a certain variable. This communicates that we need to find the derivative with respect to x. We are tipping our hat to the variable called x. We are acknowledging that our function is going to be defined in terms of x. If you saw this, again, it is a command saying, take the derivative. But this time we're not going to tip our hat to x, we're going to tip our hat to the variable t. So it could be that you have an equation defined in terms of t, and you're going to find the derivative of that thing. This means take the derivative with respect to t. So you're going to see this command in this form. It's going to be d over dx of x squared equals y, or something like this, right? This means take the derivative of your equation with respect to y. So it's as if we're kind of going to distribute this thing, and by the way, I'm going to give this thing another name. I'm saying a lot of things about this, and I understand that there's a lot going on here. But I'm going to go ahead and call this thing a differential operator. A differential operator. An operation like addition or subtraction in our world now is the act of taking the derivative. And so this thing is an operator telling you to do the work of differentiating. So if we take d over dx of x squared and set it equal to d over dx of y, let's go ahead and start with the right-hand side. The right-hand side becomes dy over dx, which we've already talked about is equivalent to y prime. This means that I have successfully found the derivative of y with respect to x. So to complete this, I need to take the derivative of x squared with respect to x, which is 2x. And technically, if we think about our chain rule, I have taken right now the derivative of the outside, evaluated at the inside, and if I take the derivative of what's inside with respect to x, I'm left with dx over dx, which is interesting. It's kind of like I'm multiplying d over dx times x and getting dx over dx, which is 1. So I don't really need it. This is awkward. All right, so we're going to take the derivative of x. So here we go. It's sort of like this x is being divided by 1, and we're multiplying d over dx times x over 1. So we're going to have dx over dx, which is 1. All that to just reiterate the point that I made back here at the bottom of this page. Okay, so let's take the derivative of 2xy plus y, which equals 3. This, again, reminds us to take the derivative. That means take the derivative with respect to x. So this is going to get a little bit weird. When we take the derivative of 2xy, we need to use the product rule because we have the product of 2x multiplied by y. So I'm going to start by just rewriting this differential out in front of each one of these terms. And if we apply the product rule to 2x times y, we're going to have the first times the derivative of the second. And so we need to ask ourselves, what is the derivative of y with respect to x? And it's dy over dx. So that's the first times the derivative of the second, plus the second times the derivative of the first. The derivative of 2x with respect to x is equal to 2. So that part's good. And here's this addition, and now we need to add the derivative of y with respect to x, which is simply dy over dx. And this will all equal the derivative of 3. The derivative of the constant with respect to x will always be 0. The goal is to find the derivative of y, which is dy over dx. And the problem right now is that we have two dy over dx terms. So we're going to go back to Algebra 1 land and factor this thing out. And it's going to look like this. So I've just moved 2y to the other side. And now we can see that I have a common term of dy over dx that I can factor out. And doing so will leave me with 2x plus 1. Alright, so to solve for dy over dx, we're going to divide each side by 2x plus 1, and we are done. So the derivative of y with respect to x is negative y over 2x plus 1. And you should notice a couple of things. One of them being that if we started out with an implicitly defined function where x and y are all garbled together, we will end with an implicitly defined function where x's and y's are all garbled together. All right, one more example. We are going to find the derivative of x plus y squared equals y. So I'm just going to blast through this one here. The derivative of x with respect to x is going to be dx over dx, which we know is 1. And when I get to this y squared thing, I am going to have to consider the fact that my inside function is not x. It's speaking a different language than the variable that we are trying to pay homage to. So we're going to have to use a chain rule. We're going to apply the chain rule and take the derivative of the outside, evaluate it at the inside, times the derivative of what's inside, and the derivative of y with respect to x is dy over dx. And this whole thing equals the derivative of y with respect to x, which is dy over dx. So at this point, again, the goal is to solve for dy over dx. We want to isolate dy over dx. So I'm going to pull all of the dy dx terms onto one side of the equal sign and factor them out, or factor it out. So I've subtracted this guy over to the left-hand side of the equal sign, and I want to get rid of this 1 by moving it over to the other side. And now at this point I can factor out my common term of dy dx. And this leaves me with 2y minus 1 equals negative 1. And the final step, I'll move over here, the final step is to divide each side by 2y minus 1, and we now have the derivative. Bam.